Hi everyone, this is Yan. In previous chapter, we discussed that the raw data of 100 school children's weight and age won't make sense to us unless we organize and summarize them. The methods to organize and summarize the raw data are descriptive statistics, and frequency distribution is one of the methods. So what is a frequency? Frequency describes the number of times that a score or an event occurs. Frequency distribution is a summary display for distribution of data. Here is an example on page 32 in our text. If you are given this table of 15 numbers of American children's TV time per day, what are you going to do first? First thing we'll do is to put them in order in the frequency distribution table. There are two columns. We put in the X column the 50 numbers from the largest to the smallest and from the top to the bottom. In the Y column, we put in the frequency count for each number. Then we find out about the real range of the data set. The largest number is 175 and the smallest one is 0. So the real range is 175 minus 0 plus 1, which is 176. We put the numbers in order, but there are still too many numbers to look at. What about group the numbers into 10 groups or 10 intervals? 10 is an arbitrary number that we decide to use. It's neither too many nor too few in this case. It all depends on the size of the data set. The range of each interval is called the interval width. The way to calculate it is to divide 176 by 10, which is 17.6. All the original numbers are whole numbers, so to maintain the same degree of accuracy, we round 17.6 up to 18. Now we grouped the 50 numbers into 10 intervals, and each interval width is 18. We have a simple frequency distribution table. For each interval, there are the interval boundaries, the lower and the upper boundary. 0 is the lower boundary, and 17 is the upper boundary. What we need to pay attention here is that the largest number in the original data is 175. The upper boundary for the top interval is 179, which is not in the original data. But the number 175 is in the 162 to 179 interval. Now let's summarize the rules to construct a simple frequency distribution table. Each interval is defined by the interval boundaries, the lower boundary and the upper boundary. And all interval widths are the same. And intervals, they don't overlap. We need to maintain the same degree of accuracy as the raw data. That's why we rounded 17.6 up to 18 to make sure the interval width is a whole number. And make sure when you add up the frequency counts, they are the same as the original data set. That's an example of how to construct a simple frequency distribution table. We created a frequency distribution table of ungrouped data and then grouped them into 10 intervals. In our text, there is not a large data set to show how to run SPSS for grouped data. But if you have a large data set, there is a feature in SPSS to define the interval width so you can group your data. This screenshot is just from a website on the internet, and to show you how to use this feature in SPSS. This is the example 2.1 on page 36 in our text. These are the employees' safety complaints against 45 local small businesses over the past 3 years. We put all 45 numbers in the order from the largest to the smallest and divide them into 8 intervals. And then we put their frequency count in the next column, and we get a simple frequency distribution table. When you add the frequency counts from top down or from bottom up, you will get a cumulative frequency. If we want to know how many businesses belong to the dangerous category with more than 99 complaints in the past 3 years, we'll use the top-down method. Add up the frequency counts of the top 2 intervals. 2 plus 5 is 7. So we know there are 7 businesses that belong to the dangerous category because they have received more than 99 complaints in the past 3 years. If we want to know how many businesses have received less than 62 complaints, we'll use the bottom-up method. We'll add up the frequency counts of the bottom 2 intervals. 3 plus 3 is 6. And we know there are 6 businesses that can be considered safe because their employees have fewer complaints. So whether you accumulate a frequency distribution from the bottom up or from the top down, it depends on how you want to discuss the data. In simple frequency distribution and a cumulative frequency distribution, we distribute frequency counts. But when we handle larger data sets, we use relative frequency. To calculate relative frequency, we divide the frequency count in each interval by the total frequency count. For example, for the top interval 108 to 116, the frequency count is 2. The total frequency count is 45. So to calculate the relative frequency for the top interval, we divide 2 by 45, we get a 0.04. A relative frequency is a proportion from 0 to 1 that describes the portion of a data in each interval. So if we add all the relative frequencies up, the total should be 1. To make it easier to understand, we can convert the decimals to percent. We'll get relative percent. 0.04 times 100 is 4%. And if we add up all the relative percents, we'll get 100%. In simple frequency distribution and a cumulative frequency distribution, we distribute frequency counts. In relative frequency distribution, we distribute the proportion of scores in each interval. In relative percent distribution, we distribute the percentage of scores in each interval. We can also summarize relative frequencies and the percents cumulatively either from bottom up or from top down and construct cumulative relative frequency distribution and cumulative percent distribution. Only the bottom-up calculation is shown here because we need the bottom-up numbers for the next slide and I ran out of space. I won't repeat the calculation process here, but you can pause for a few seconds to go through the numbers. We also have a new column of real limits in this table, which we'll discuss in the next slide. So what is real limit? Our measurements of the complaints are all whole numbers, and our precision of measurement is 1 unit. Mathematically, an observed value of 90 would be obtained when the real value is between 89.5 and 90.5. And the observed value of 90 actually represents a range of real values from 89.5 to 90.5. So these values are called the real limits. Same for the value of 98. The real limits are 97.5 to 98.5. Same for the interval of 90 to 98. The real lower limit is 89.5 and the real upper limit is 98.5. And the difference between the real upper and the lower limits is the interval width, or the real range of the interval. And in this slide, our problem to solve is to find out the value of the score at the 75th percentile. First, we need to find out where the 75th percentile points belongs. 75% is more than 61% and less than 85%. So the 75th percentile point is located in the interval of 90 to 98. And the real range for this interval is 9. The range from 61% to 85% is 10 plus 14, which is 24 percentage points. The 75th percentile is 10 points from 85th percentile. So 75% is 10 out of 25 of the total interval width, 9. So it is 3.75 points from the real upper limit. So the value at the 75th percentile point is 98.5 minus 3.75, which is 94.75. Instead of tables, we can display frequency data in graphs. For continuous data, we can use polygon, ogive, and histogram. For discrete and categorical data, we can use bar charts and pie charts. Both polygon and ogive are dot and line graphs. In polygon, the dot represents the midpoint of each interval distributed on the x-axis, and the y-axis represents the frequency. In ogive, the dot represents the upper boundary of each interval distributed on the x-axis, and the y-axis represents the cumulative percent. The difference between a histogram and a bar chart is that the bar chart is nothing more than a histogram with separated bars, which makes it more appropriate to summarize discrete and categorical data. And what I like about the pie chart is it gives you a holistic view of the big picture. Thank you for listening. Please let me know your questions and feedback.